Today in this lecture, we are going to introduce the concept of duality theory and the dual simplex method. We say that every LPP, if you consider, has a corresponding mirror image formulation. That is, we can make a mirror image corresponding to every LPP, which we call as the dual problem corresponding to a simplex problem corresponding to the primal problem. If a primal problem has n variables and m constants, we know it already, we have seen number of variables and number of constants. So, if one LPP has n variables and m constants primal problem, then its dual will have just the opposite one, that is m variables and n constants. So, please note this one, that if the primal problem is having the n variables and m constants, then the corresponding dual problem will have m variables and n constants. You can think that LPP as a resource allocation problem, where we have to maximize the profit or revenue, whatever you say, subject to some constraints on the consumption of resources. If this is the primal problem, that I have to maximize the profit or revenue subject to the constraints on consumption of resources. In that case, in the dual problem, what we have to do? In the dual problem, we have to minimize the consumption of the resources subject to the conditions or subject to the profit maximization constraints. So, if you see, it is just the opposite of the dual problem. In this example, whatever I was telling you, resource allocation, in the primal problem you are maximizing the profit subject to the constraints on the consumption of resources. Just opposite thing in the dual, that is, you just minimize the consumption of resources subject to the profit maximization constraints. So, one may ask, in both cases, whether you are solving the primal problem or you are solving the dual problem, you will get the same result. The result for both the problems must be same. So, the question may arise, why should I go for dual and then find the solution? Instead of that, I can directly formulate the LPP and solve it by the algorithms whatever we have learned till now. The point is, if you have less number of variables and more number of constants in the original problem, then if you convert it into its dual, then it will have the less number of constants and more number of variables. And we know that if the number of constants are less, then computational effort also will be less, because less number of constants has to be checked for they are satisfying the criteria or not. So, basically we use the dual problem whenever we are having more number of constants and less number of variables. So, that the dual will have the opposite one, the more number of variables and less number of constants. And to handle the computational problem, we convert a primal problem into corresponding dual problem and then solve the problem into by this method. Some interesting features you may observe. One is, number one, if you take any feasible solution of the dual model, I am just writing any feasible solution of dual model provides a bound on the objective to the original problem. So, dual model provides a bound on the objective to the original primal problem. So, basically if you have a solution, feasible solution of dual model, in that case there must have a bound on the objective function of the corresponding primal problem. Now, number 2, these all are the theorems. Optimal solution of a dual, is equals to again optimal solution of the primal problem is equals to optimal solution of the primal problem. So, as I was telling you that the original primal problem model and the dual model both have the same solution. Number 3, dual of a dual model is once again the original primal problem. Dual, if you take dual of a dual model, dual of a dual model is once again the original primal problem, original primal problem. So, if you take the dual of a problem, in that case first you are taking the dual of original model, and then again if you take the dual you will come back to the original model. So, these are the some theorems which are necessary. These things I will show you through the examples also. The primal dual formulation can be shown by this table like this way. You have the primal problem, what would be the corresponding dual. You have this primal and dual. Suppose you have a minimization problem, minimize C transpose x subject to A x greater than equals b, obviously x is greater than equals 0. Its dual problem will be, since if the function in primal is minimization, in dual it will be just the mirror image, as I was telling, that is opposite one. Maximize these objective functions, as I was telling you, maximize B transpose y subject to A transpose y less than equals C transpose, where your y is greater than equals 0. So, if you see in the original problem, you was basically minimizing the vector C associated with the decision variables x subject to the constraints which were given by the x greater than equals b, satisfying the b vector. But in the dual problem, you are maximizing the constraint side b rho B transpose y subject to, you are satisfying the constraints, the cost associated with the x, that is A transpose y less than equals C transpose. This is one form. The other form, you can maximize C transpose x subject to A x less than equals b, x greater than equals 0. In this case, it will be minimize, again same way, B transpose y subject to A transpose y greater than equals C transpose y is greater than equals 0 over here. So, if you see here, the C transpose x is maximizing subject to A x less than equals b. Here you are minimizing B transpose y subject to A transpose y, here the constant has become greater than equals C transpose. So, just the mirror image or the opposite one you are considering. So, this is the primal problem, and so this is the original matrix form we have written. Now, the canonical form of the LPP in both primal form and dual form. Already we have done the primal form, canonical form, that is maximize z equals C1 x1 plus, from here it will be more clear to you, C1 x1 plus C2 x2 plus Cn a n subject to A I1 x1 plus A I2 x2 plus A I n x n less than equals B I, where your I is 1, 2 like this way up to m, x I is greater than equals 0, I equals 1 to m. So, you are having n variables over here, and since I is varying 1 to m. So, therefore, we are having m constraints on the left hand side. B vector B consists of B1, B2, Bm. So, what will be the associated, therefore, we say that the x1, x2, xn, these decision variables are called primal variables and z is the corresponding primal objective function. The associated dual model of this problem is, this was a maximization problem. So, this will be mean, say w equals, you can use any variable, summation over I equals 1 to m b I v I, that is b 1 b 1 plus b 2 v 2 plus b m v m, subject to a j 1 v 1 plus a j 2 v 2 like this way plus a j m v m greater than equals c j. Your j is equals to will vary 1 to n and your v 1, v 2, v n all are v m all are greater than equals 0. So, here if you see in the primal problem you had n decision variables x 1, x 2, x n, whereas in the dual problem you are having m decision variables v 1, v 2, v m. So, you are minimizing this b 1 v 1 plus b 2 v 2 like this, that is the left hand side b row of the constants of the original problem you are taking, and the constants will be changing a j 1 v 1, a j 2 v 2, a j m v m, that is vector a remains the same greater than equals, here it will come as c j, that is for the first constant it will be c 1, for the second constant it will be c 2 and like this way. So, here you have to note that v 1, v 2, v m we are calling as dual variables and w we call the dual objective function. So, I think it is clear now, whenever I am having a problem in canonical form, how to obtain the corresponding dual form. So, in the canonical form usually we take the variable in the less than equals type. So, if the constant is greater than equals type, then we have to convert it into greater than less than equals, that is if I have say summation j equals 1 to n a I j x j greater than equals b I is there. In that case, I have to convert it into like this, summation j equals 1 to n a I j dash say x j less than equals b I dash, where your a I j dash equals minus a I j and b I dash, this is equals minus b I. So, whenever you are having greater than equals type, then convert it into less than equals type. Note one thing here which I will discuss again afterwards. If you remember, in the whenever we try to solve the simplex problem, value of b I is always positive. This restriction is not there in the corresponding dual problem. Why? We are solving, value of the corresponding b I may be negative, may be positive, it can take any value, whereas in the primal problem always it will be taking b vector will take only positive values, whereas in the dual model it may take any value, that is positive or negative values it may take. You may have another equality constant also, that is summation j equals 1 to n a I j, this is a I j x j, this is greater than equals b I. Whenever you are having these two, this I am sorry I have written wrongly, this is equality constant. You may have less than equals, for canonical we need less than equals. Whenever you are having the greater than equals, you are converting into less than equals the way we have told just now, and whenever you are having the equality constants, these equality constants can be written as the two inequality constants like this, summation j equals 1 to n a I j x j is less than equals b I. To upper half space you can consider summation j equals 1 to n a I j x j greater than equals b I. So, whenever you are having the equality constant, then this equality constant has to be written in this form, and this greater than equality again can be converted into less than equality by multiplying minus 1 on both sides. So, if the equality is there, you convert it into this, so that you can come to the canonical form, and from the canonical form you write down the corresponding dual model. Note one thing, in the if both in primal and dual model consists of only inequality constants, then that model is known as, we call it as symmetric LPP. We call this one as symmetric LPP. If both the primal and the dual problem have only inequality constants, whereas if the primal and dual is having only equality constant, then that problem is known as unsymmetric LPP. Then that one is known as unsymmetric LPP if both primal and dual is having only the equality sign. And the third point is, if the problem both primal and dual is having both equality and inequality constants, in that case we call it as mixed LPP. We call this one as mixed LPP. So, for symmetric LPP, the constants will be either less than equals or greater than equals. For unsymmetric LPP, the constant inequality will be only equality. For mixed, it can be either less than equals or greater than equals or only equality constant. Just two theories I will tell, I will write down two theorems which will be useful for you. We will not give the proof, you can see any book for the proof of this thing. If I am just writing, it will be easier. If any constant in primal is strict equality, then corresponding dual variable is unrestricted in sign, So, if you see, every constant of the problem of the primal problem corresponds to a dual variable in the dual problem. We are saying that if any constant in the primal problem has equality sign, in the constant has equality, then the associated or the corresponding dual variable must be unrestricted in sign. Unrestricted in sign means, I want to say here, suppose you have a variable a greater than equals 0, you have another variable b is also greater than equals 0. Now, if you are writing c equals a minus b, then definitely we cannot tell what will be the value of c. C may be 0, may be greater than 0, may be less than 0, and that is the reason we can say that c is unrestricted in sign. So, whenever you are subtracting one positive variable from another positive variable, the values are not known. Therefore, I do not know what would be the result. In that case, we say that one variable will be unrestricted in sign. We will see that one, if it is unrestricted, how to handle the cases. Theorem 2, if any variable of the primal problem, if just opposite of the earlier theorem, if any variable of the primal model, is unrestricted in sign, then the corresponding constant of the dual will be an equality. That is, if in the original problem some variable is unrestricted in sign, then the associated constant of the dual will also be associated with that particular variable, whatever constant is coming in the dual problem, that will be equality in sign. So, these two theorems are just the opposite of this one. Now, let us take few examples how we are obtaining the solution of different or not solution, how to find out the dual of a primal problem. Let us take one easy problem. Maximize z equals 3x1 plus say 2x2, 3x1 plus 2x2 subject to 3x1 plus 4x2 less than equals 22, 3x1 plus 2x2 less than equals 16, x2 less than equals 3 and x1 x2 greater than equals 0. So, if you see it is a maximization problem and the constants are all less than equal. So, I do not have to change to anything, it is already in the canonical form. So, since I have 3 constants, if you see, then 3 dual variables will be associated with each constant. Say I am telling for the first one V1, for the second one V2, for the third one V3. So, 3 dual variables will be associated with this. So, what I will write down, its dual will be minimize say W. So, what we have done here, if you see in the theory, I have already told it would be B transpose into y means here we have taken V1. So, minimize W will be 22 V1 plus 16 V2 plus 3 V3. So, minimize W is 22 V1 plus 16 V2 plus 3 V3. I think it is clear. The coefficients of the vector V you are taking and you are associating with the dual variables V1, V2, V3. So, V1 is associated with the first constant, V2 is with the second constant, V3 is with the third constant. So, you are minimizing W equals 22 V1 plus 16 V2 plus 3 V3 subject to what will happen. Now, you have to take the columns over here, that is this is the first column over here 3x1, x1 is appearing only first constant and second constant. So, it will be 3 V1, this 3 V1 plus 3 V2, nothing is there. So, 3 V1 plus 3 V2, this is greater than equals the first one, that is 3, the C1, here your C1 is 3. So, this is your C1, this is your C2. So, for the first column you are taking the first column 3 V1 plus 3 V2 means corresponding to the row what is the variable, what is the dual variable is associated, you are taking the coefficient of that 3 V1 plus 3 V2 greater than equals 3. So, next one will be 4 V1 plus 2 V2 plus coefficient of x2 is 1 here. So, plus V3, that is 4 V1 plus 2 V2 plus V3. This will be greater than equals C2, here C2 cost coefficient it is 2. So, C2 and V1, V2, V3 greater than equals 0. I think it is clear now. If you see the problem minimization, minimize W equals 22 V1, this you are taking row vector, first you are associating dual variables corresponding to each constant. First constant we have denoted by V1, second one V2, third one V3. So, your objective function is it was maximization. So, minimize W equals 22 V1 plus 16 V2 plus 3 V3 subject to you take the first column, first element is associated with the variable V1. So, 3 V1, next element is associated with the V2. So, 3 V1 plus 3 V2, then nothing is there. This will be greater than equals this C1, that is 3. Next one will be 4 V1 plus 2 V2 plus V3 greater than equals C2, that is 2. So, for the original problem or primal problem corresponding dual, this is your dual problem. If you take the dual of this problem again, you consider the dual of this problem. Whenever I want to take the dual of this problem, you see I am writing in short maximize, say I am writing Z, what will happen? Say for this constant I am associating x 1, for this constant I am associating the variable x 2. So, it will be maximize z equals 3 x 1 plus 2 x 2 subject to you take the first column, that is 3 x 1 plus 4 x 2, 3 x 1 plus 4 x 2, this will be, this was greater than equals. So, it will be less than equals C 1, here for the dual C 1 is 22. You take the second column, for the second column it will be 3 x 1 plus 2 x 2, then V 2 is 3 x 2. So, 3 x 1 plus 2 x 2, this is less than equals C 2, C 2 is 16, and for the third one B 3, first 2 is not there, only B 3 is associated with x 2. So, x 2 less than equals C 3, that is 3, and obviously x 1 x 2 greater than equals 0. So, you have the original problem, you are taking the dual. Again, if you take the dual of the original problem, again you will go back, get back the original problem. That is the reason in the theorem we have told dual of a dual is the primal. Again, the theoretical proof is also there. We have shown it through the example that the dual of a dual is primal. Again, let us take the second problem. Minimize z equals x 3 plus x 4 plus x 5 subject to x 1 minus x 3 plus x 4 minus x 5, this is equals to x 2 minus x 3 minus x 4 plus x 5, this is equals 1. Your x j is greater than equals 0, j equals 1, 2, like this way 5. If you see, the first thing is the problem is not in a canonical form, we have to convert it. Here it is minimization, so we have to convert it into maximization, and the both the constants are equality constants. Since from the theorem again, if since we have two equality constants, so therefore, correspondingly dual we will have two unrestricted variables. We will see how it is coming. Very first thing is we have to convert it into canonical form. So, this equality has to be broken into two inequalities, one will be with less than equals, another will be with greater than equals. So, I am writing the canonical form of this one, maximize z star equals minus x 3 minus x 4 minus x 5. You are subject to the first one will be x 1 minus x 3 plus x 4 minus x 5 less than equals 2. The other one will be greater than equals 2, and we will multiply by minus 1. So, that it again becomes the less than equals. So, it will be minus x 1 plus x 3 minus x 4 plus x 5, this is less than equals minus 2. Similarly, the second one also we have to write down x 2 minus x 3 minus x 4 plus x 5 less than equals 1, and the other one will be minus x 2 plus x 3 plus x 4 minus x 5 is less than equals minus 1. Obviously, your x j is greater than equals 0, j equals 1, 2, like this way 5. So, this is in the canonical form. Now, you can write down the dual of this one. You have 4 constants. So, therefore, in the dual problem you will have 4 variables. In the original problem you are having 5 variables, 2 constants, 5 variables and 4 constants. So, say this is dual corresponding dual variable I am writing, this is W 1, W 2, this is W 3, this is W 4. So, what will be the corresponding dual? I am just keeping it here, not here. What will be the dual problem? For the dual, if you see here, you have to minimize some function, I am writing minimize d equals, your dual problem objective function will be then 2 W 1 minus 2 W 2 plus W 3 minus W 4. This will be the objective function 2 W 1 corresponding to B vectors, as I told you earlier, 2 W 1 minus 2 W 2 plus W 3 minus W 4. So, we are writing now 2 W 1 minus 2 W 2 plus W 3 minus W 4. So, this one subject to, let me put it in this way, then it will be easier for you, I think. Yeah, subject to this one is coming. So, minimize 2 W 1 minus 2 W 2 plus W 3 minus W 4. Subject to, now you take the first column of these constants, that is what will happen here, that is subject to x 1 is there only in 2. So, W 1 minus W 2 greater than equals 0, W 1 minus W 2 greater than equals 0, x 1 is not there in other equations. For the second one, x 2 is there only associated with W 3 and W 4. So, W 3 minus W 4 greater than equals 0. Then you take the third column minus W 1 plus W 2 minus W 3 plus W 4. So, I am sorry, yes, this is okay, because why this is greater than equals 0, I forgot to tell you. That is, if you see this one, there is no coefficient corresponding to x 1 and x 2 here, that is C 1 is 0, C 2 is 0, for this reason these two are greater than equals 0. Now, for the third one, that is corresponding to x 3, it will be minus W 1 plus W 2 minus W 3 plus W 4. Okay. Minus W 1 plus W 2 minus W 3 plus W 4, this will be greater than equals, this is the third one. So, C 3 means coefficient is minus 1. So, it will be greater than equals minus 1. Similarly, for x 4 also you will write down W 1 minus W 2, W 1 minus W 2 minus W 3 plus W 4 greater than equals. Again, if you see C 4 is minus 1 here. So, it will be again minus 1, and the last one will be minus W 1 plus W 2 minus W 1 plus W 2 plus W 3 minus W 4 greater than equals, the coefficient will be C 5 corresponding to x 5. So, it is again minus 1. So, it will be minus 1, and obviously, your W j is greater than equals 0. So, corresponding to this problem, your dual is this one. Your, if you see, the dual is this. We have told one thing, W j is greater than equals 0, it is true, but in the original problem, in the constants you have two equality constants. So, according to the theorem, there should have two variables which are unrestricted in sign, but you are saying here that all are greater than equals 0. What happens now? Say you take W 1 minus W 2 equals V 1 and W 3 minus W 4, this is equals V 2. If I take this one, your constraints will be changed to, these constraints will be changing to V 1 greater than equals 0 from the first one, next one is V 2 greater than equals 0, next one is minus V 1 minus V 2 greater than equals minus 1, next one is V 1 minus V 2 greater than equals minus 1, last one is minus V 1 plus V 2, minus V 1 plus V 2 greater than equals minus 1. So, you are writing in terms of V 1 and V 2 now the problem. What about the sign of V 1, V 2? V 1 is the difference of two positive numbers, V 2 is also the difference of two positive numbers. Therefore, you cannot say actually what would be the sign of this V 1 and V 2. So, V 1 and V 2 you have to declare as unrestricted in sign. So, here basically once you are converting it, substituting W 1 minus W 2 equals V 1 and W 3 minus W 4 equals V 2, then V 1 and V 2 variables will be unrestricted in sign. So, this dual problem again you can write in terms of V 1 V 2 as minimize D equals twice V 1 plus V 2 subject to minus V 1 minus V 2 greater than equals minus 1, V 1 minus V 2 greater than equals minus 1 minus V 1 plus V 2 greater than equals minus 1, and V 1 greater than equals 0, V 2 is also greater than equals 0. So, you may ask the question, what about the unrestricted in sign? You told V 1 and V 2 unrestricted in sign, right. Here from here you can always tell that V 1 comma V 2 are unrestricted in sign, right. But you have this condition V 1 greater than equals 0, V 2 greater than equals 0. So, basically this unrestricted in sign condition is now redundant for this problem, but this may not be true for every problem. For this problem V 1 V 2 unrestricted in sign is redundant, since from the condition already we know V 1 is greater than equals 0, V 2 is greater than equals 0. That is the reason we have written V 1 greater than equals 0, V 2 is also greater than equals 0, but we have not talked about the unrestricted. The reason is this one, this unrestricted condition is redundant, since already I know these two variables V 1 V 2 are greater than equals 0. So, this is another type of problem. Let me take up the third type of problem, a mixed problem, that is say minimize Z equals x 1 plus x 2 plus x 3 subject to x 1 minus 3 x 2 plus 4 x 3, this is equals 5, x 1 minus 2 x 2 less than equals 3, 2 x 1 minus x 3 greater than equals 4, and x 1 x 2 greater than equals 0, x 3 is unrestricted in sign, x 3 is unrestricted in sign. So, if you see we have considered one equality constant, one less than equals, one greater than equals, and in the primal itself one variable is unrestricted in sign. So, from the theorems again, since the first constraint contains the equality sign, therefore, the corresponding dual variable will be unrestricted in sign. Similarly, there is one variable unrestricted in sign in the primal problem. So, in the associated constant in the dual problem, there will be equality sign. So, it is just vice versa. If you have one equality constant corresponding to that, whatever dual variable is there, that will be unrestricted in sign, and if some variable is unrestricted corresponding to that, in the dual problem the corresponding constant will be of equality of sign. Now, unrestricted variable x 3, this is x 3, I cannot write it in the canonical form. So, x 3, because for canonical form the variables must be greater than equals 0. So, I can write down x 3 equals x 3 dash minus x 3 double dash, where x 3 dash and x 3 double dash both are greater than equals 0. The problem is, so now x 3 we are substituting x 3 by x 3 dash minus x 3 double dash, where both x 3 dash x 3 double dash are positive. So, x 3 is unrestricted in sign and we are converting it like this. Let us write down the corresponding problem. Maximize z equals then minus x 1 minus x 2, this was a minimization problem, minus x 3 dash plus x 3 double dash, subject to x 1 minus 3 x 2 plus 4 into x 3 dash minus x 3 double dash. One will be equality is there, I have to convert it into inequality. Next one will be minus x 1 plus 3 x 2 minus 4 into x 3 dash minus x 3 double dash less than equals minus 5. Next inequality will remain as it is, less than equals 3, and the next one I have to convert. So, minus twice x 1 plus x 3 dash minus x 3 double dash, this is less than equals minus 4, where x 1, x 2, x 3 dash and x 3 double dash all are greater than equals 0. So, now we are bringing it back to the canonical form. So, please note that whatever problem is original problem is given to you, first you convert it into the canonical form and then write the corresponding dual of that particular problem. Now, I think you can write down the dual of this problem of your own. Here you are having how many constants? You are having V 1, V 2 like this way. So, I can write down here, I can take V 1 dash, this is V 1 double dash, this is V 2, this is V 3, I can denote it. So, what is the corresponding dual now? Your dual problem would be, as I was telling you, 5 V 1 dash minus 5 V 1 double dash plus 3 V 2 minus 4 V 3 associated with the B vectors, and the problem will be minimize Z star say this is equals 5 V 1 dash minus 5 V 1 double dash plus thrice V 2 minus 4 V 3. So, 5 V 1 dash minus 5 V 1 double dash plus 3 V 2 minus 4 V 3, subject to again you take the columns of this. So, if you take the columns, then it will be V 1 dash minus V 1 double dash plus next one is V 2 minus twice V 3. This will be greater than equals the first coefficient is your first coefficient is minus 1, C 1 is minus 1. So, it will be minus 1. You take the next one, I think you can see it properly. Then you have to take the column for x 2, that is minus 3 V 1 dash plus 3 V 1 double dash, then minus twice V 2, x 2 is not there in the next row. So, this will be greater than equals, again the coefficient corresponding to x 2 is minus 1. So, it will be again minus 1. You take the fourth column, in the fourth column it is 4 V 1 dash minus 4 V 1 double dash, after that x 3 is coming on the fourth row. So, plus V 3 greater than equals, again it is minus 1 for corresponding to x 3 dash. So, it will be this one. The last one is you take the last row, that is minus 4 V 1 dash plus 4 V 1 double dash, after that where I am coming x 3 dash 4 V 1 this one minus corresponding to this minus V 3, which is greater than equals 1, because corresponding to this x 3 double dash you are having this is as 1. So, these are the 4 columns you are getting, minus 4 V 3 dash minus plus 4 V 1 double dash minus V 3 greater than equals 1, and of course, V 1 dash, V 1 double dash, V 2 and V 3 all are greater than equals 0. So, this is the corresponding dual. So, dual you got it from the original problem. Now, you substitute say V 1 equals V 1 dash minus V 1 double dash. So, the problem, this problem again can be written as minimize Z star, this is equals 5 V 1 plus 3 V 2 minus 4 V 3, subject to then V 1 plus V 2 minus twice V 3, this is greater than equals minus 1. The next one is minus 3 V 1 minus 2 V 2, this is greater than equals minus 1. If you see this one, these two I can multiply 1 by minus 1 and I can get the less than equals and then I can make it equality. I am writing at a time, that is 4 V 1 plus V 3, this is equals minus 1. These two clubbing together, last two equations, I am getting one equality constant like this way. And here your V 2 greater than equals 0, your V 3 is greater than equals 0, but what is V 1? V 1 is difference of two positive numbers. So, therefore, V 1 is unrestricted in sign. V 1 is unrestricted in sign. I think the method is how to convert the corresponding dual problem into this is quite clear to us. So, V 1, V 2, V 3 we are getting. So, as I have told in the original problem, since if you see this one, there was one equality constraint corresponding to this one variable will be associated, will be unrestricted. So, here V 1 is unrestricted in sign, and since one variable was unrestricted in sign, in the dual there will be one problem which is equality in sign. So, I hope you can do convert one primal problem into dual or the other way round. Now, just again see one table when I can find the solution. You have a primal problem, you have the dual problem, and what is the conclusion? Number 1 is both primal and dual problem is having feasible solution. So, what would be your conclusion? Finite optimal solution for both primal and dual exists. I am not writing this one. If both primal and dual is having feasible solution, then our conclusion will be finite optimal solution exists for both primal and dual problem. Now, say primal has no feasible solution and dual is having feasible solution, it may happen. In that case, what will happen? Dual objective function is unbounded. Please note this one. If the original problem is primal problem has no feasible solution, dual is having feasible solution, it implies that the dual objective function is unbounded. Similarly, the other way round, that is primal problem is having feasible solution, dual is having no feasible solution. In the same way, you are telling primal objective function is unbounded. It means primal objective function is unbounded. And another one is both is having no feasible solution? Since both are having no feasible solution, so obviously the solution does not exist here. In this case, solution does not exist of that particular model. So, you have to see these parts. So, the first thing what we have done, that is how to find out the from the primal problem, how to find out the corresponding dual problem, and now let us come to the other one, dual simplex method. Just 1 minute, I think before going to the dual simplex method, let me just take this example, it would be better for me. Before going to the dual simplex method, we will come to dual simplex method, this one. You see this particular problem, that is maximize z equals 3 x 1 minus 2 x 2 subject to x 1 less than equals 4, x 2 less than equals 6, x 1 plus x 2 less than equals 5, minus x 2 less than equals 1, and x 1 x 2 greater than equals 0. So, your original problem is maximize z equals 3 x 1 minus twice x 2 subject to x 1 less than equals 4, x 2 less than equals 6, x 2 less than equals 6, x 1 plus x 2 less than equals 5, minus x 2 less than equals minus 1. First, we want to write down the dual of the problem, and then we want to solve the problem. What is be the dual? Obviously, there are 4 constants. So, 4 variables will be associated with this. So, this is V 1, this is V 2, this is V 3 and this is V 4. So, dual of the problem is minimize say W, this is equals 4 V 1 plus 6 V 2 plus 5 V 3 minus V 4, 4 V 1 plus 6 V 2 plus 5 V 3 minus V 4, we are getting this one subject to your this one is V 1 x 1 is there again in V 3. So, V 1 plus V 3, V 1 plus V 3 greater than equals your C 1 is here 3. So, V 1 plus V 3 greater than equals 3. Then for the next row x 2 is not there. So, it is V 2 plus V 3 minus V 4. So, V 2 plus V 3 minus V 4 greater than equals C 2 is minus 2. So, it is minus 2, and of course, your V I is greater than equals 0, where I is equals to 1 to 4. But again if you see, if I try to find out the solution of this problem, one method is you convert it into the standard form and then you may try to find out the solution of this. What is in the standard form? It is maximize W equals minus 4 V 1 minus 6 V 2 minus 5 V 3 plus V 4. Now, you introduce the variables 0 into x 5 V 5 plus 0 into V 6 subject to V 1 plus V 2 V 1 plus V 3 minus V 5 equals 3. I am writing directly actually, then minus V 2 minus V 3 plus V 4 minus V 6, this is equals 2, again V I greater than equals 0. What I have done? I have first written it in the standard form that is maximization problem. This greater than equals I have converted into less than equals. Then I am introducing the slack variables V 5 and V 6, and now I can find out the solution of this canonical form the way we have done it earlier. You see this table, C j is there. So, what will be the entering vector? Entering vector will be here subject to this. So, V 5 and not V 5, V 1 and this will be minus or this will be plus actually, plus V 6, because you are introducing this one here after changing it. So, it will be A 1 and A 6. If I take A 1 and A 6, V 1 and V 6. So, it is A 1 and A 6. So, it is your V 1 and V 6, C j values are minus 4, minus 6, sorry you cannot see it, I think now it is okay, minus 4, minus 6, minus 5, 1, 0 and 0. So, your C b values will be minus 4 and 0. Your B values are coming as 3 and 2. Now, write down the rows as usual, that is 1 0 1, 0 minus 1 0 and 0 minus 1 minus 1 1 0 and 1. If you compute the, I have to compute the ratio also, this I have not written, Z j minus C j value if you calculate, I am not saying these things, that is 0 6 1 minus 1 4 and 0. So, your entering vector in this case will be this F 4. If you calculate the ratio, this is 2. So, therefore, this is the outgoing vector. So, for this one again you can calculate from here. So, your B will be A 1 and A 4. So, it is V 1 and V 4. I am just writing the table minus 4, minus 6, 5, 1, 0, 0. C b value is minus 4, 1. I am writing this 3, 1, 0, 1, 0, minus 1, 0. I am not explaining because already we have done it so many times, we have explained properly. So, 0, minus 1, 1, 0 and 1. If you calculate Z j minus C j values, it will be 0, 0, 4 and 1. So, now all Z j minus C j is greater than equals 0. So, we obtain the solution. But see, since it is a dual problem, solution will not come from here. Usually it comes from here, but for the dual case it will come from here, that is your V 1 is 4 and V 2 is 1 and your value of W in that case will be 0. And obviously, V 2 is 1. So, V 1 is 4. Sorry, this is totally wrong. From here the solution of the dual, if you see solution I am writing in this page, solution of the dual is V 1 equals 3, V 2 and V 3 is not there, V 2 is 0, V 3 is 0, V 4 equals 2. If you calculate W star will be 10. This is the solution for the dual problem. For the primal problem, what will happen? For the primal problem, you have to take the data from this side, that is your x 1, you have two variables x 1 and x 2. So, x 1 will be 4, x 2 equals 1. So, your x 1 is 4, x 2 equals 1. If you calculate value of z, that again you will get 10. So, please note that for the dual problem, whenever directly you are solving, for the dual variable solution you will obtain as usual. For the primal variables, solution will be coming from this side. Thank you. Next class we will go through the simplex approach.